Hello and welcome to the session. Operating Systems LO5. Be able to write programs at the kernel level. Have you ever wondered how operating systems interact directly with hardware? Kernel-level programming is the key to this interaction. This video explores how to write programs at the kernel level, focusing on Linux. Discover the tools, techniques, and examples needed to master this advanced programming skill. Kernel modules extend the functionality of a running kernel without rebooting the system. They interact with hardware like block and character devices. Examples include device drivers and resource monitors. They enable system calls, bridging user-level and kernel-level tasks. Learning how to write and manage these modules is crucial for system programming. To start kernel programming, you'll need a Linux OS, such as Ubuntu. Essential tools include GCC, make, and kernel headers. A virtual machine is recommended for safe testing. These tools allow you to write, compile, and test kernel modules. Proper setup is vital for successful development. A simple kernel module can log messages when loaded and unloaded. The code includes initialization and exit functions. Use printk to display messages in kernel logs. Compile the module with a makefile. This example demonstrates basic module functionality. Developing kernel modules involves writing low-level code. These modules interface with hardware or manage resources. Linux is commonly used for educational purposes. A structured guide helps in creating simple modules. This skill is essential for extending operating system capabilities. Kernel modules include device drivers and system call extensions. They can monitor resources like memory and CPU. File system modules are another type. These modules enhance the kernel's functionality. Understanding their types aids in selecting the right module for your needs. System calls are crucial for kernel and user-level interaction. They allow user applications to perform privileged operations. Writing system calls involves editing kernel source files. These calls provide a controlled entry point into the kernel. Proper implementation extends kernel functionality. To add a system call, first define it in a source file. Register it in the syscall table with a unique number. Declare it in the syscall's header. Recompile the kernel to apply changes. This process allows user space to access kernel functions. Kernel modules can interact with hardware using specific APIs. Examples include writing drivers for USB devices or network cards. Interactions may involve reading hardware registers or handling interrupts. Memory management is also crucial in these modules. Proper interaction ensures efficient hardware communication. Testing in a virtual machine prevents system damage. Avoid direct user space memory access without checks. Clean up resources like memory and devices. Use GPL-compatible licenses for code distribution. Following best practices ensures safe and efficient kernel module development. Kernel-level programs can perform various tasks. Examples include device control and custom logging. They interact with hardware and monitor system resources. System monitoring tools are another application. These tasks highlight the versatility of kernel programming. Debugging at the kernel level is complex but essential. Bugs can cause system crashes or memory corruption. Common issues include memory management and concurrency errors. Debugging tools help identify and fix these problems. Effective debugging ensures code stability and performance. Kernel debuggers like KGDB allow source-level debugging. Print logging traces execution flow. Crash dump analysis helps after a system crash. Dynamic debugging tools offer runtime analysis. Static code analysis detects bugs at compile time. Stability testing involves stress and fault injection tests. Performance testing measures I, O, and interrupt latency. Memory leak checks ensure proper resource management. Profiling helps identify CPU-intensive functions. These tests ensure the kernel code is robust and efficient. Use virtual machines to test new kernel code. Modularize code for dynamic loading and unloading. Maintain logging discipline for readability. Document code changes and use version control. These practices support effective kernel development. The Hello kernel module is a simple example. It logs messages on load and removal. The code includes initialization and exit functions. Compile with a makefile and test in a VM. This example demonstrates basic kernel module creation. A kernel module can read system time. It uses the kTime_getReal TS64 function, logs the current time in kernel logs, compile and test similarly to other modules. This example shows interaction with system resources. Kernel-level programs can control devices and log system events. They interact with hardware and monitor system metrics. Examples include flashing LEDs or reading sensors. System monitoring tools report memory usage. These tasks showcase the power of kernel programming. Debugging ensures kernel code stability and performance. Use low-level debuggers and runtime tracing. Static analysis helps find bugs early. Performance profiling identifies bottlenecks. Mastering these tools is crucial for kernel development. Security is vital in kernel programming. Validate user inputs to prevent exploits. Keep system call logic simple and robust. Avoid memory leaks and kernel crashes. Security ensures safe and reliable kernel operations. Kernel-level programming offers powerful system capabilities. By mastering tools and techniques, you can extend kernel functionality. With careful coding, you can safely perform low-level operations. This knowledge bridges user and kernel space effectively. Embrace the potential of kernel programming. In conclusion, the ability to write programs at the kernel level is an advanced skill that requires a deep understanding of operating system architecture and low-level programming. Kernel-level programming enables direct interaction with hardware, memory, and system processes, allowing for the development of device drivers, system modules, and performance enhancements. Mastering this skill supports efficient system control, optimization, and the development of robust operating system components. Thank you for watching this video. If you have any questions, please feel free to contact us via email or WhatsApp at 074843 61688.